All right, everybody, welcome to part two of our Transformers from a Mechanistic Interpretability perspective. And today we're going to be talking about the attention mechanism, which is a core part of a transformer.
And like always, we're going to pause frequently and we're going to gather questions before moving on. But if you have questions at any time, you guys should not be hesitating to ask at all. This is fairly Socratic. So we strongly encourage to ask anything you're confused about any open time, no matter what it is.
Exactly. Yeah, we'd much rather answer a question now than have it boil and then 10 slides down, you have no idea what's going on.
All right, so we're going to cover first, talk about tokenization, which is a great segue from what we covered last time. We're going to move into the motivation behind why we need context in our embeddings. And then we're going to talk about positional encodings and what they even mean. And then subspaces, information that can be found inside them, intuition behind attention, and then we're going to get a really good attempt at formalizing what this concept of attention is inside transformers.
Yeah.
All right, so first, let's review what we learned during last lecture. So transformers are the fundamental architecture behind large language models. Okay, anything that you see online, GPT, Llama, BERT, these are all models that are built for understanding natural language tasks. That's what an LLM is. And LLMs, the whole point is that we represent these words as these higher dimensional vectors. And last time we talked about how these vectors were the embeddings for the word. And then the embedding space is basically the structure of all the different embeddings the model learns at any given time. And its embedding space has structures and patterns that develop while the model trains. And then we talk about the patterns that we found inside the embedding space, semantic syntactic similarity. We talked about some of the cool hypotheses around this. And then finally, we talked about transformations to the embedding space as a conceptualization for what the transformer does. Cool. And then last time, we basically talked about the embedding space and the patterns that it can pick up. Words that are similar to each other, that have shared grammar, they'll be closer together in this embedding space, right, guys? But then the frequency of the word's linearity, these are all patterns of the embedding space. But one thing that we failed to replicate is the meaning understanding of the words that can shift dramatically based on the context that we find them in. For example, we found a sentence that said, I went to the river bank, versus I withdrew money from the bank. Then the meaning of the word bank shifts a lot from the first sentence to the second sentence. But the embedding space we talked about last time had no way of encapsulating this information. For as far as we know, these two banks are the same. So this is a fundamental flaw in our current architecture, and we're going to take some time to correct it today. Okay, so any questions so far about what we covered last time? We're all good? Okay, cool. So last time we talked about how words turn into embeddings, right? But one thing that we didn't really talk about specifically is the semantics of how this happens. I remember last time Emma had a question and she was asking, hey, if you had a word that was Alex Ning, right? How is it considered as one word is considered as two words? I just mentioned that last time, it's basically how we tokenize the word. And so what is tokenization? Well, one token is an individual unit of language that the model can process, right? So for example, if I had a sentence, the roots of education are bitter, but the fruit is sweet, we might tokenize this as each word becomes one token, very intuitively. That's how we might tokenize the word. But sometimes when a word is really big, we might tokenize it as two separate words. We might tokenize ineffective as the prefix in as one token, and the word effective as the second token. And why do we do this type of tokenization? Well, the idea is for efficiency and generalizability. And we'll talk about this more in a future example. Do people understand kind of what tokenization is, even if they don't understand why we do them yet? Okay, cool. And the really important thing that I want to motivate you guys, so if you guys get one thing out of this lecture, it's that context is fundamental to understanding language. Because without having contextual awareness to our model, there's no way that we can empower to do the context and the tasks that it needs to do for the higher level performance that we need. Think about it this way, without giving context, we're not letting the model know that other words are important. At any given time, we're only focused on one word at a time. So how do we understand sentences? How do we understand paragraphs? How do we understand stories? we need to be able to understand words beyond just that singular meaning of it. We want the meaning of a word to depend on other meanings of other words, right? We need this, and we'll talk about why this is so powerful. Let's take the example, I went to the river bank. Well, this is our embedding space. We talked about how this looks like last time, right? We want to have bank to be closer to the words like water, dam, words that signify the meaning behind river bank. But we don't want bank to be close to words that are like money or account or dollars. Unless we say a sentence like I withdrew money from the bank, in which case we want the red arrow, not the green. In this case, context matters. We need to know about the existence of the word money to understand where the embedding for river bank goes. In the same way, if we want to do let's eat grammar, or let's eat grandma, we want to make sure that hopefully grandma isn't up there with turkey, food, and burgers for Thanksgiving, right? We want it to be close to dad, family, and mom. And the only thing that can help us distinguish that is this right here, the comma. So we want our token to consider that comma, right? Or else this is what we're going to end up getting out of our model. And let's go back to our initial example of tokenizing words. If I tokenize words in a certain way, like if I tokenize impossible as im and possible, now the model is able to understand that this idea of possible is basically moved towards this negative connotation words, immobile, imperfect, impervious. In this way, it has understood the concept of the prefix im, right? It understands what it means when we put the word im in front of it, right? This is why tokenization is really important. Because by tokenizing the word in certain ways, we're able to give additional context to the word. We generalize to all negative words, not just what impossible means in that situation, but imperfect, impervious, immutable. We know what all these mean now. Does this make sense? Yeah.
When we're training an LLM, do they actually like segment out the im from like impossible and all those words? Like
Yeah, it depends on the tokenizer that you use, right? So the tokenization is like an algorithm that basically takes the word that we end up having and tokenizing that into a list of separate tokens. So
what I was wondering is,
yeah,
like, there are words that start with im that aren't like a negative on something else, right? Like, I don't know, like immolate or something, like that's setting something on fire. That's not like a negative of doing something.
or maybe impact, for example.
Yeah.
Right. Yeah, so in that case,
do they tokenize those words, or do they?
Yeah. So like you said, that depends on the tokenizer that you use, right? But it certainly could get tokenized that way, right? And so in that case, well, you need a model. You need a model that's more sophisticated, right? You need a model that understands that that im in some contexts means like the negative, right? But not with all contexts, for example. So when it sees, molate, right? Then the im doesn't mean the opposite of whatever molate means. It just means that those two should go together to mean one thing. Yeah.
So yeah, the tokenizer that you use needs to be sophisticated, must be like a learned.
When you do attention, can it see what's after it?
Aha,
That's a good one.
That's a great question.
That's a great question.
So we're not going to get into that today.
We're gonna talk about that next
yeah,
time, though.
but basically, for the models for generative models, for example, like ChatGPT, the answer is no.
The answer is no. We'll talk about this.
It
Yeah.
doesn't have the other. It doesn't have the encoder layer.
Huh?
Because ChatGPT doesn't have the other. Like it only has.
Yes,
Exactly.
yes.
Exactly.
Wait, what was the?
Sorry.
What was the last verse?
His last question is, can the model, for any given word, right? Can the model see the tokens that follow that token, right? So for example, for possible, right? The embedding for possible can see the embedding for im, right?
But can't see what comes afterwards.
Yes, but can the embedding for im see the embedding for possible? And the answer is for most generative models, the answer is actually no. But that's for next time.
Okay, cool. Any other questions? Okay, we're good. All right. So, yeah,
All right, yep. Okay.
sure. So, matter a sentence of words to order in. Does everyone understand what I just said right now? No, it's kind of gibberish, right? So the whole point is the order in which I'm speaking to you guys matters a lot. The words that I'm sending to you guys, English language, any language in any world, the order of the words that we deliver in matter a lot, right? So how crucial is the order for words to human language? Very crucial. Without order, we can't understand anything, right? So how can we expect our model to understand it when we don't give it the words in the right order, right? But everything we talked about until now, we never talked about order in the embedding space. Because everything the model understands is kind of like this embedding space, right? If we don't imbue that embedding space with the concept of order, it won't understand the natural order between human language. So right now, there's no way that we encode position in our embedding space. So how can we fix this in teacher models? Anyone have any ideas? That's fine. Basically, like we do with everything else, right? When we do semantic similarity, we want to make sure the words that are similar together or closer together, right? What do we do with frequency of the words? We showed how we can get the embedding space to look like what we want it to look like, right? We're going to do the same thing with position. We're going to find some way to reflect and encapsulate this idea of position inside our model, right? And we call this positional encoding. So again, this is another extraneous thing or external thing that will be used to imbue positional understanding within the model. There's different algorithms that can be used, sinusoidal positional encodings are the most common or the most easier to understand, but we're not going to get into much details. For now, I want you guys to understand that these positional encodings are just methods by which we get the model to understand the sequentialness of the words that we give it, the sequentialness of the tokens that we give it, right? Does it make sense? Okay, cool.
All right, now let's talk about extracting subspaces. So this is just a quick review of last time. All right, first thing, what are transformations on vector spaces? So a transformation on a vector space, aka just a transformation, is a function. That acts on vectors in a certain vector space. For example, a transformation on a 3D vector space is a function which changes 3D vectors. Transformations can retain the dimensionality of vector, or they could also increase the dimensionality or decrease it. So you have a 3D vector. It could say a 3D vector. It could become a 4D vector, or it could become a 1D vector. Right. Furthermore, subspaces. So a subspace is a lower dimensional vector space that exists within a high dimensional vector space. So here we have this 3D vector space. We notice that both the plane, which is a 2D subspace, and the line, which is a 1D subspace, are both subspaces of the 3D vector space. Furthermore, we have projections. So this is a kind of linear transformation which decreases the dimensionality of a vector space, right? And a little bit of nuance is that this is also from last time, but a linear transformation can be a composition of a projection as well as other linear transformations, which include things like scaling rotations and shearing. So, you can have a linear transformation which reduces the dimensionality of the vector space. So that linear transformation may involve a projection, but it may also include other kinds of linear transformations. And yeah, so here is an example for the projection. So say that we have a projection that acts on a 2D vector space, which projects onto the y-axis along the x-axis, right? So what does that mean? Well, say we have this vector in 2D space here, and its coordinates are 2, 4. That means in the x direction, it has a length of 2, and then in the y direction has a length of 4, right? So a projection onto the y-axis along the x-axis is equivalent to eliminating the x component and only retaining the y component here. So basically, we take this vector, we get rid of the x component by projecting it, or by just shifting it along. Thus, that there is no more no more x component like such, and then now, and then the resulting vector would be a vector in 1D space with just the direction 4, right? So this is just the same thing here. Once again, we have this vector. We want to remove the x component and only keep the y component like so. And then this is the same thing, but just with
Just the numbers
the coordinate.
right?
Keep the second coordinate and remove the first one. All right, lots of questions?
Yeah, this is everything that we kind of covered last time, right? Just how projections work in general. Does this make sense to everyone? Okay, perfect.
Okay, now let's visualize subspace extraction. Oh, sorry, I think one thing actually I didn't mention last time here, right, is basically, so we're going to use like the term extracting a subspace a lot. But basically what we just mean is when we extract a subspace, right, that's when we do, you know, some sort of linear transformation that reduces the dimensionality such that we keep that subspace and we get rid of the rest of the information. Okay, so, you know, does the term extract make intuitive sense for you all?
We're just taking information that we want.
Exactly.
From a vector space.
Yep.
That's what we're just taking the information that we want. That's all.
Cool. Okay, so now let's visualize the subspace extraction, since the rest of our slides will make
A lot more sense.
Yeah, exactly. They'll make heavy use of these visuals. So say we have some vector here, right? With n dimensions. We can extract a subspace by simply taking a few components or dimensions of this vector and removing the rest. So say we choose, you know, to take the first 4, right? This is right. The result is that we have extracted a 4D subspace of this vector, right? Now, just for some nuance, these subspaces don't have to align with the dimensions that we choose to represent the vector with. For example, something like this would also be extracting a 4-dimensional subspace, but of course, it's a lot more it's a lot more convoluted. But for simplicity, when we visualize this, you know, we're going to visualize extracting a subspace like so, right? So when we do something like this, it doesn't say that, you know, we have this generalized visual of a vector on the left, right? And then here we just visualize extracting some subspace, right? Now, it does not mean that we only extract, you know, like these dimensions from the representation of the vector that we have. It just visually what we're trying to say here is we just extract, you know, some smaller subspace.
We're just taking some dimensions. We're just extracting some subspace.
Exactly.
Really generally.
It could be something like this or like that. Yeah.
Yeah.
But either way, the idea is we extract a smaller subspace. Right. So for example, here we extract disjoint subspaces, right? Here we extract subspaces with
some amount of overlap.
Exactly.
Right.
And then finally here we extract subspaces with different dimensionalities, right? So one's larger than the other. Cool. Does all that make sense so far?
So we're good on this side. We're about on this side. We're good here.
Fantastic. All right, and finally, a review on matrix multiplication for linear transformations. So this is also from last time, but the basic idea is mathematically linear transformations on vectors can be computed by matrix multiplication, right? We're not going to cover how this is done, but the idea is, you know, just know that conceptually all matrix multiplications perform some kind of linear transformation.
So we see multiplication by a matrix thinks, okay, there's some projection, there's some shearing, there's something involved.
Yeah, exactly. Right. And then just a recap of the previous slides. So certain kinds of linear transformations which do dimensionality reduction allow us to extract subspaces of a vector, right? And then once again, the nuance, along with extracting a subspace, a linear transformation can simultaneously also do other kinds of linear transformations on the vector too, right? So intuitively, what that might mean is, you could, one linear transformation could first extract some subspace of your vector, and then also perform some further linear transformations on that extracted subspace, right? And finally, we can represent linear transformations as matrices, which we multiply by the vector to perform linear transformations. And then one more important nuance. This is literally the same thing. We really wanted to hammer this home, and the reason was that because we're going to use the term extracting a subspace, and we're going to leave it at that. But we want to make it clear that when we say that, just subconsciously know that more can also be happening, right? But to keep things intuitive, we're just going to use that one term to keep things simple. All right, questions?
Main idea is, main idea is to review the projections we just talked about and what that means for matrix multiplications. Does that make sense to everyone? Okay, cool. All right, so let's talk about subspaces of information, right? So this is the kind of example that we saw last time, right? We kind of have this embedding space where words that are very similar were grouped together as different embeddings were in different embedding spaces. Now we have different subspaces that store different kinds of information within this embedding space, right? We're going to talk about exactly what this is.
Sorry.
Yeah. So let's just focus on bikes for now, just one word in the embedding space, right? Then we notice that, in one dimension, we kind of control the category that we're looking at, right? We're looking at vehicles, we're looking at fruits, right? Because if we remember on the previous slide, we kind of had, all the vehicles on the left-hand side, we had all the fruits on the right-hand side. So in the X dimension, we kind of control the categoryness. And then plurality is controlled on the vertical axis, right? Which means that as the higher that you go, the more singular the words are, the lower that you go, the more plural that the words are, right? Do we all remember this example from last time? So in this example, so in this example, we have that the y-axis controls plurality and the x-axis controls category. So we can actually break this down into the separate subspaces therewith, right? So the x-axis subspace is going to contain information regarding the category. And the y-axis subspace is a subspace that contains information about the plurality of what we're looking at, right? So basically, when we just extract the x-axis, right, we're preserving only the information that we care about the category, right? So when you think of a bike in your head, you might think of, the color of the bike, is it broken? How rusty is it, right? But somewhere when you think about a bike, you have this thought that, oh, it is a vehicle, right? Like the bike is a vehicle. So when we extract the subspace, that's all we're taking from the bike, not the entire complex understanding of what everything a bike is. Oh, it's red. It's like this. I fell off the bike when I was like 10 years old, doing something, right? I'm only taking that one information, the categoryness of that bike.
Exactly. So notice here, we don't know whether this is singular or plural, right? It's just the concept of bike.
Just bike. And in other words, right, the y-axis preserves only information about plurality. Right. So when you think of bikes, think about the only thing you know about it is, the fact that there's many of them. Right. So when you only isolate plurality, we only take into account the one thing that signifies that it is indeed plural. And in this case, we basically have this idea that the subspaces of an embedding space codify. The subspaces of the embedding space are codifying the different concepts and features that we talked about last time. Right. So we have this entire embedding. Let's say this embedding is for an object, some random object, right? So we might have a subspace that has to do with the flexibility of that object. You might have one that deals with the texture, the color, and then you might have another one that kind of deals with the vibrancy, the resilience, so on and so forth. The main takeaway here is that subspaces can store information, right? Hopefully this was a pretty natural conclusion from what we already knew from last time.
Yep. And notice that here, for example, that vibrancy is, vibrancy has some overlap with both the color as well as the texture subspaces, because vibrancy is, to some level, is determined by a combination, both the color and
How colorful is
the
it?
texture.
How does it look?
And same for resilience, which has some overlap with both texture and flexibility. Questions?
So main takeaway, our embedding space stores information in subspaces of itself. Make sense? Yes.
This might be like related online, but do embedding spaces try to like be efficient in that they will store color, vibrancy, and like always a texture separately? They'll try to see how they can optimize them, or is that just...
Definitely. Let's see.
That's a good question.
Yes.
Per word though, like, can you generalize that to like everything?
Yeah, you basically, the model has this understanding representation about where it stores like different features like an embedding space, right? And the way it'll learn that will kind of be up to the model, right? So it will learn like where to store different like features in kind of the way that makes the most sense for it, the way that makes the easiest or efficient way for it. The trick is, what does it mean for it to be efficient? What does it mean for it to follow the path of this resistance? That might vary.
Sure.
Yeah. For example, like, so, that not only depends on what, these qualities are, but also what the task is, right?
Exactly.
Say that you train your model and you train the embeddings using a task that only cares about vibrancy, right? And doesn't separately consider color or texture, right? Then the model, might not really have a great understanding of color or texture separately, right?
You'll need to distinguish between the two, right? And allocate an entire subspace kind of,
Yeah, exactly. So how much space, how much subspace the model will give to one certain quality, one feature, completely depends on what the task is, as well as what the model finds is
it's the most intuitive way,
efficient.
or the
Yeah.
least balanced, which again is a little bit debatable because who are we to tell the model what the easiest way is?
Yeah.
Right. But yeah.
Okay. Well, this is the really fun part now.
Okay.
Yeah, this is so. Yeah, we'll.
Yeah, we're gonna proceed with giving you guys intuition behind attention, right? And yeah, attention, we're gonna first talk about why do we want this, right? And the main thing I want us to keep in the back of the head is we want context. I was gonna convince everyone in this room that context is really important, right? And the one thing that you guys also have in the back of your head is by imbuing context, we want our embedding space to codify context, to encapsulate this idea of context throughout this entire space that we do. So think about that when we talk about the slides that follow, right? So the embedding is everything we have. This is everything that we understand about the concept of river. You might have something that talks about how water is flowing, other parts that talk about different ideas, but when you think of river, what do you think of? That's what the model has to codify into this embedding of river. Right? That's all the space that we have for river. Same way, this is through the embedding that we had for bank. In our early example, I went to river bank. This embedding is kind of our entire representation for this concept of bank. Okay. So we agree on that so far. And like we just talked about, these different subspaces store different things about each embedding. Right? We just talked about that as well. So what does that mean? Well, if you want to create a contextually aware embedding, you want each word or each token to understand and to be aware of the other tokens, right? When you think of riverbank, the bank that you think of is not the bank that people rob. It's the bank that is sitting on the coast of the Nile, right? It's the bank that you think about, sitting somewhere in a river. Our understanding of bank has some understanding of river that's imbued into it. They're not disjoint. Does it make sense? So in this case, what we really want is we want to update everything we know about our bank and redefine it with some information from river. We're going to redefine our definition of what bank is with some of what we learned from river. And by doing this, we'll say that bank is now contextually aware. It's aware of what it means because it means something more than just what we initially thought it was. It now has understanding from the concept of river also. Does this make sense? Okay. And now when our model thinks about the idea of bank, right? It's also going to think about intuitively, it's going to think about this concept of river because we've ingrained it within the subspace of bank. So why does this happen, right? Why does moving content from one river to another word end up getting the model to think about these and associating them close together? Well, yeah. So think about what happened. We just overwritten one subspace and we introduced information from another subspace, right? And subspaces are just dimensions and directions in an overall vector space, right? So at least in some dimensions, we've taken this concept of river and brought it really close to wherever bank was. Or we've taken this concept of bank and we drew it really close to wherever river was, right? We've moved them together. Maybe not in the overall, maybe like not crudely, but in some dimensions we definitely did. Does it make sense? So yeah, I'll give you some little bit of time to digest that. But basically the idea is we want to create contextually aware embeddings. We do this by taking context from one embedding and moving it into another embedding. Information from one embedding to that into another. And when we overwrite one subspace with information from another subspace, we change the vector, right? So we change only some of the dimensions in the vector. We bring these dimensions closer to that other vector that we wanted. And in what this looks like in our embedding space is we move this embedding closer to the first embedding that we want. So now we bring the word bank to where it's supposed to go, next to river, because that's the context that we have. Does it make a little bit more sense, guys? You can get thumbs ups if it's good. Okay, we're good.
Right, yeah. And so we wanted to tie this in with the linear representation hypothesis that we talked about last time. And specifically, so we've been talking about subspaces and extracting them and that kind of stuff, right? Yet the visual example that we had here, for example, there's not really a subspace here. And the reason is because in 2D, it's just hard to show like taking on subspace. Like there are 2 dimensions in total, right? So here, for example, basically we just moved bank in the direction for river, right? So it's kind of hard to see, oh, like what's the subspace, because we used, we moved it in the direction of just the whole embedding for river, right? But linear representation hypothesis really shines when we talk about transferring subspaces and components of embeddings, which modify the makeup of the other embeddings. So we wanted to give an example that really motivates this, right? So say we have a 3-dimensional embedding with kind of the following components. So the first dimension, the x dimension, is the dimension for bank, right? So that contains information about bank. The y contains information about river, and the last, the third dimension contains information about animal, right? So for example, so under the system here, we have that the embedding 1, 0, 0 refers to bank, right? 1, 1, 0 refers to river. Did I say 1, 0, 1, 0?
Yeah.
And then you get the point, right? And then we also have, we can take combinations of these, right? So for example, river bank 1, 1, 0 is just bank plus river, right? And fish 0, 1, 1 river plus animal. Cool.
Yeah, this follows as a consequence of linear representation hypothesis we talked about last time.
Yeah.
Right.
Now say we have the sentence, I was caught fish. I caught fish at the bank. Right. Now in this case, we want bank to develop the context of river bank. You're probably not catching fish at a financial institution. So what we want to do is we want to extract the subspace of fish corresponding to river, right? And then add the context to bank, right? So say we have the embedding for fish, right? We only want to extract the subspace related to river, right? We don't need the information related to animal, right? So then we take that subspace, right? Which, by the way, that subspace would be the y-axis, because it's the second dimension, right? Then we take that subspace and we add it to the embedding for bank, right? And then finally, we get the embedding for riverbank. Does that make sense?
Yes.
So in this case, would riverbank be like a separate token from bank with like its own embedding?
In this case, the riverbank is kind of a conceptual idea, right? It's this concept of what we want our bank to be close to, right? The idea is that when we end up shifting bank in a direction with river, where it ends up is what the idea of riverbank should be. Okay.
Yep. And that's separate from what tokens you have in your vocabulary. We're really concerned about what the model, understands. Understands internally.
Right. Got
it. Yeah.
Okay. Cool. So back to our example. So now we can understand what's happening when we're taking this concept of river and putting it into bank, right? We're basically doing something that Alex just said we're doing, right? We're taking some concept of river, right, that actually matters to the context at hand, and we're updating this context of bank. And now that we think about river, you're also thinking about, we're not thinking about bank, we're also thinking about the river bank. We're not just thinking about, just a financial institution. Right?
Exactly. But let's say that this sentence was actually longer. So, for example, oh, sorry, we have the sentence here. Never mind. Yep.
So basically, in this case, we kind of had, river just pass its embedding to just bank, right? But we want to create contextual aware embeddings, right? So we really want to have river send its information to all the words that we have in our sentence, not just bank, right? Because that's what being aware of context is. When we read sentences, we take in all the words together at once to make meaning from it, right? It's not just, oh, bank comes up river, therefore it's a river bank, right? It's no, I am also at the river, right? So because of that, we want to be able to, send the subspace of river to all the different words that we have here.
Exactly. And of course, so we can't just we can't just just simply send that context, right? But we also have to be careful about how much context we send to each example, right? Because because some context matters more for some words than others, right? In this case, the word bank, right, really needs that context about river, right? Whereas the word to probably needs it less.
It doesn't need that much.
Exactly. Yeah. That word to, the definition and the understanding the model has of the word to, it's already, it's pretty good. Right. So therefore, right, when we send this, this context, we basically scale it, right?
We have to scale, we have to tone it down for certain words.
Exactly.
We don't really need it that much to understand what it means.
Yeah.
Right? So does this make sense so far? And we'll talk exactly about how this stuff is going to work more in detail. But for now, at least the main takeaway is we want to create contextually aware embeddings. Means we take context from one embedding and send it to the rest. And when we send context, we can't just send the raw form all at once. You have to tone it down in cases where you don't need it as much.
Yeah. And so also one distinction that we want to make right now is that between the source embedding and the destination embedding, right? Because because
in this case,
exactly, because we want each embedding to send its context to all of the other embeddings, right? So each time this happens, one embedding will act as the source embedding, and the rest will act as the destination embeddings. And so of course, so when we do this, all tokens will need to have the chance to act as the source embedding.
right. So we're not just going to be sending river to all the words in the sentence. We have to take the subspace from every single word and set into the dimensions of every single other word that we have. Yes.
In something like this, do all of the words have the same features as their embeddings? Like, are they all parallel?
What do you mean by parallel?
Like the first feature of the embedding for I is the same as the first feature for the embedding of lent, or am I just thinking about that?
No, because the main concept is when we extract a subspace from these tokens, right? We are basically taking some information from them,
Well,
right?
I'm just saying like embeddings as a concept, like they're all in the same space, right?
Yeah.
So
All the
feature
embeddings.
one is the same as feature one in all the words.
So, do you mean like the first, sorry, the first dimension?
Yeah.
Yeah. So
Like basically the
so
feature geometry.
yes. So they would all be in the same space. But this is one thing that we talked about last time. So when we talk about language models, right? We use the word features very liberally. So because traditionally, for example, features could just you have a number of features corresponding to the number of inputs that you have, right? But for language models, and when we talk about this kind of stuff, features really just mean concepts, right? So features could be a concept that's mentioned in the input sentence, or it could be a concept that's not that's not explicitly mentioned in that sentence, but that the model should be able to infer. For example, some examples of features could be the concept of happy, sad, fire truck, bad grades. The third thing, or the third thing in a sequence, right? So they could be something that's more concrete, or something that's very abstract.
But like the fact that moving in this direction means that we're closer to this feature, for example, that template will stay the same. Right? That feature geometry.
Correct.
So when we're feature sharing like between bank and all these other words, like they already own those dimensions. It's just a matter of updating their values.
Yes. So I think what basically, so when you add these, like when you add this, when you add some subspace to I, right? That subspace means the same thing to I as it means for went.
It's the same linear independent directions that
Exactly. Yeah. But same, but basically like same vocabulary. As far as
same vocabulary.
the vector space goes.
Yeah.
Great question. All right.
On that note.
More questions? Yes.
Yeah, so with something like fish in bank, do they know to inject more context because of that river connection? So like, is it like based on amount of subspaces that they share like directional similarity to, that they know how to inject?
That's very insightful. Yeah, we'll talk about this in more like detail in the next couple slides, right? But the main idea is that words that are similar together will extract, obviously we'll have more information that they will extract from, right? But yeah, we'll talk about this in future slides.
Yes.
Yeah, we'll get to this.
Yeah. How you choose the amount of information that you transfer is one of the main points here. Yeah.
The main points.
We'll get to that.
We'll work up there. Yeah.
Yeah.
Thanks. Cool. Anyone else? Are we good? Okay, cool. All right, so let's simulate what this looks like for a sentence of length 3. Right? Like I said before, we want each of our words to take a subspace and send it to each of the other words. Right? Because again, we're trying to create context-aware embeddings for all the words, not just for one. So we'll take some subspace, we'll take it from I, we'll take it from like, we'll take it from cats, and we're gonna project that into our subspaces, a different subspace for I like cats, for each of the different ones that we have, right? So the subspace for I will go into I like cats. The subspace for like will go into I like cats, and it'll all go into the same subspace for each of the 3 cases.
Exactly. So so here in this diagram, we're looking at for each source, right? We're taking a sort of a perspective from the source token, right? So The embedding for I will go to all three words. The embedding for like will go to
All three words, and the embedding for cat.
will go to all three words.
Yeah.
But what if we take, a perspective more focused on the destination, right? So for each of the embeddings, right, what from the other three embeddings will be added to that that embedding, right? So we end up with this here, right? So for the embedding for I, that will we will add three components, right? From all three of the embeddings to I. Same thing for like, and same thing for cats.
So nothing changed on this diagram, everything's the same, just flip it
Exactly.
upside down, yeah. Does it make sense? Okay, we're good so far.
Fantastic.
Right,
Okay.
and let's just, consider the portions without, or just consider the portions that are being added to each embedding for now, right? So just, the context from I being added to I, context from like being added to like, so on and so forth, just the portion that we're adding to each one. Okay. And
So now we've just rearranged them, same thing here, right? So the portions that are being added to I there, they're now the first row. Portions that were added to like, second row. Portions added to cats are
the
in the third row.
yeah,
Yeah, just rearrange, but still the exact same concept.
is everyone good so far? We're just moving things around. Yes.
For the some of the green squares are like colored in less, or they're like closer to white than like a deep color. Is that like
We're
a
taking
scalar
less
multiple?
yeah.
Is that the
exactly.
scalar multiple on how much is being transferred to the other word?
Yeah, that's kind of the way you want to think about that.
Exactly.
Yeah.
Yep, exactly. Yeah, so here the lighter colors mean less of that, and the dark colors mean more.
For example, for cats, we're gonna take a lot from cats, not as much from like, but maybe a little bit more from I. That makes sense?
And would that be like symmetric? Like if I is taking a very little from cats, would cats be taking very little from I?
Not necessarily.
Not necessarily.
In fact, there we go. Right. The colors just represent the coefficient.
Like you just mentioned, we're just gonna change from colors to like numerizing like the colors that we have.
So now just get rid of that filled in the color, right? So
So far things just still make sense.
yes.
Right? Okay, we're good so far.
Cool. Okay, and just to remind, right, what's going on. So example, we take a lot from I, not that much from like, even less from cats, right? We're gonna sum that up and then we'll go
To update our understanding of what I is, we're gonna take some from like, some from cats, update understanding of like, and update our understanding of cats. So now these three, we're gonna say they're contextually aware, right?
Mhm.
Okay?
Cool.
Cool.
still same thing, right? We've
Just added
gotten
some boxes around it.
exactly, we've gotten rid of the plus signs here, but still the exact same thing.
Yeah.
Right. Yeah.
So let's just use the coefficients, forget about everything else.
This is the attention pattern.
Boom, right? So basically what we've just came up with is the transformation that we would use to because remember matrix are just transformations, right? This is basically what we're going to use to transform our regular embeddings into contextually aware ones, right? Yeah, again, nothing changed. That's all we really looked at.
Okay, cool.
Cool.
So
And each row here is a probability distribution that sums to 1 that describes how much of each embedding is making up each sum. Right? So row wise, they'll all add up to 1 as we need. And like I said, it's the same thing. So for the first row, for example, we'll understand that, for I, it's going to be 70% I, 20% like, and 1% cat, for example. And in the case of fish and bake, it'll be different numbers, right? And so on and so forth. Yeah. Are we good so far, guys? Yes.
Why is it a probability distribution?
Be more interpretable. Because now that you have probability distribution that we have, some scalar value, it allows us to multiply it and get some expected value out of it.
Why is it called probability?
the definition of probability distribution is just something that sums to 1. So
Yeah.
a group never sums to 1. Yeah. Cool. Okay. Yeah. So now the question is great.
How do we create this, right?
Other questions? All right. Okay, so so we're gonna make a quick note now, right? So far we've tried to motivate mechanisms with purpose before we actually explain them, right? For example, in other words, we've taken an interpretation first approach, right? We try to explain why we need something before we explain how it works, right? But the following explanation for how we create the attention pattern will be mechanism first. And the reason is that interpretation first explanations really work well when we can fully interpret and fully and completely justify how a mechanism works, right? But the full variety of methods in which models use their attention mechanisms is still very much unknown, right? Thus, we will lead with the mechanism, right? And then try to motivate, and then try to motivate how that mechanism may be used.
So yeah, I guess the question is, do we do a good job of explaining and motivating why we need the attention pattern? Okay, now we'll talk exactly how we get to the attention pattern.
Yep.
Right.
So first thing, this is just a review from last time. So the dot product, basically this is just a way of multiplying two vectors to produce a scalar, which just means a single value, right? One value. And basically, the more the vectors point in the same direction, the larger the value will be. And for example, if the angle between the two vectors is less than 90 degrees, then the dot product will be positive. If the angle between them is exactly 90 degrees, okay, a right angle, then the dot product will be 0. And finally, if it's greater than 90, the dot product will be negative.
Yeah.
And also, some for the background knowledge. So softmax, basically softmax. So given an ordered set of numbers, right? So like I don't know, whatever you want, 1, 2, 3, 4, 5, right? It converts them into a probability distribution, which means that they sum to 1, right? And one important property of softmax is that it preserves the ordering, right? So if one number used to be larger than one of the other numbers, then once you do softmax, that number will still be larger.
Yeah. And we talked about this in previous lectures as well, like softmaxers and stuff like that.
Cool.
Okay, so remember, what we're gonna do is we're gonna talk about the same thing we were talking about before, but in a different light. So from each embedding, we're gonna extract a certain subspace and we're gonna call them the queries. Okay. So from I and like and cats, we're gonna extract this a certain subspace from each of them. We're gonna call this the queries. Okay. Then from each of those same embeddings, we're gonna extract a second subspace. Okay. We're gonna call these the keys, just definitions. Right.
And then we want to just
The third time, we're gonna
make
say one more time.
third or fourth time, I don't know how many times. So we want to know. We will say extracting a subspace, but just keep in mind in the back of your mind, when you have a linear transformation, that extracts a subspace, it could also be doing more things, right?
Right.
So intuitively, what that means is that linear transformation could extract some subspace, which contains some information, and then that linear transformation could further modify that information.
In addition to getting the subspace back, we're also changing the information in that subspace that we're getting out as well.
Yeah, yeah.
That's what's happening. Cool.
Okay. Yeah. So once we have the keys and the queries, right? We're not going to line them up in this sort of grid, right? And then take the dot product between each one.
So what we're doing here is how similar is the first key to the first query? How similar is the first key to the second query? How similar is the second key to the third query? We're calculating like these AKA similarity scores for each of the different relationships that we have between each key and each query. By using the idea that vectors are closer together, we'll have a higher dot bar, right? Does this make sense so far? So that's what we're basically doing here.
Exactly. Yep. And then we call these values logits.
Yeah. And it turns out that if my key is really big, right? If I'm working with a lot of dimensions, right? Then what basically means that our dot products is going to grow like at a really fast rate. right? Like these exploding, if you know I have to dot product two vectors, and they're like 1,000 mathematically. So what we're gonna do is we're gonna divide all these logits by the square root of the dimension of each of them, right? So the dimension of our vectors, we're gonna divide it by the square root of that, and this can end up normalizing it and it'll bring the values down by a lot. We'll scale them down. So this makes them more manageable to work with. Yes.
Why are the dot products greater than one on the previous slide?
Yeah, because dot products don't have to be less one, basically. Say you have two vectors and both of them are long. So say say like both are like 10 units long and you take the dot product, it's probably gonna be greater. Yeah. All right. And then so once we divide by the square root of the dimension, then we softmax the rows. So we turn each of the rows into a probability distribution, like such. And that's it.
I feel like I've seen this before. Yeah, I don't know where it is though. Yeah.
So what is the point of dividing by the square root of dimensionality to make the numbers more manageable if you're just gonna softmax it anyway?
Yeah, that's a great question. So we didn't really want to get into the reason, but so basically the reason why, right, is softmax, you're right. Softmax doesn't care how large the values are, right? It'll always turn to a probability distribution. The thing is, the formula for softmax, right, uses these exponents, right?
Exponentials.
And
numerical.
basically what that means is say that you have say we're doing softmax on two numbers, right? 1 and 2, right? You do it and I don't know what the result would be, but you get two values, right? And one of the values would be larger, right? And then, but now let's say that you had the softmax between 1 and 5, right? You'd find that the difference, so if you compare the difference between the softmax of 1 and 2 and 1 and 5, the probability distribution for that 1 and 5, it wouldn't be, something like, it wouldn't be, a few times more different than 1 and 2. It would be many, many times different because the exponent makes that difference much larger.
You're basically magnifying the difference in the probability distributions, right? Where it should be more manageable if you divide them by the square.
So would the same be true if you did it between like 1 and 2 and like 10 and 20, for example? Would that be a different distribution?
Wait, sorry, between 1, 10
So like,
and 10,
like
20?
1 and 2 and then like 10 and 20. So like the
Yes.
same ratio.
Yes.
But different
Yeah.
size numbers.
So softmax will only consider the relative distance between the numbers. So 1 and 2 and 10 and 11 are the same. But 1 and 2 and 10, 20 are different. Now, so specifically the reason that we divide by the square root of 2, right? Is so once again with softmax, right? As that relative distance grows, right, the difference between the two values grows incredibly fast, right? And that's not great. And furthermore, basically, so the thing about vectors, right? So say you have a vector in one dimension, right? Yep, and the vector is just 1. So what is the magnitude of that vector?
1.
Exactly. So you have a vector in 2 dimensions and the magnitude is 1. Turns out the magnitude is the square root of 2. Right? Now, so you have a 1,000 dimension vector, and in each dimension that vector has a magnitude of 1, then the total magnitude of the whole vector is square root of 1,000. Right? And it turns out that as the dimensionality of these vectors grows, right? When you take the magnitudes of these vectors, and therefore when you take the dot product between them, these dot products are going to get a lot larger. Yeah, which also means that the relative difference between them are going to get a lot larger, which means that when you do softmax, it's going to start to get wonky. So we're going to scale them down just so that relative distance will decrease.
Yeah. There was another question back there.
Mhm. Did someone?
I know you have a question now.
All right, cool.
Okay, cool.
Okay, yeah, so that's it. Have,
So yeah, we basically created the attention pattern a second time, and this time we know exactly how to come to it by using the cosine similarity, which makes the assumption that two vectors that are similar would have a higher value. Right? Cool.
okay, and this is just once again a reminder of
What
the
is
function.
happening here of the attention pattern? The whole
Yeah.
point of the attention pattern is to ultimately ultimately modify our understanding of, the word I like cats to then be contextually represented, so I can move them around in mega space the way that I want to.
Yep,
Right.
and remember, for each row, we're going to basically, for example, for row 1, right, we take 70% of the context from I, row 2, 20% of that context from like, and row 3, 10% of the context from cats. But we're going to take that, we're going to sum that, and then we're going to add that to
Into
I.
that subspace that we chose.
Yeah.
Yes. Shoot.
How are our key and query subspaces chosen?
Basically, so they're learned.
That's what's learned.
Yes.
And is that the only thing that's learned in the?
No. Yes.
Well,
We'll cover that
We'll
later.
talk about this in just a
Yeah.
little
Yeah.
bit.
Yeah.
These are great questions, guys.
Yes. Cool so far? All right, great. Lots of questions. Okay, so just
You see
Real
this
quickly.
formula before, if you read a textbook, it says attention is, a function of the KQV and there's some big messy equation. All it says, I'll break it down, right, is you have the queries that multiplied by the keys, right? And then this is what creates our logics, right? Then we're gonna normalize this by dividing by the square root of the dimensionality. We're gonna pass that through a softmax to get the probability distributions. And then once we have our probability values, we're gonna update that by multiplying by the values to create our updated values, right? So that's all attention is. You can boil it all down to some really elegant mathematical function like this. Make sense? Cool.
okay, so now we're going to talk about the whole attention mechanism,
We're gonna
right?
put everything that we learned together.
Exactly. So we've talked about the attention pattern. We talked about how it's used, and we talked about how it's made. So we're going to look. So now we're just going to look. We're going to look at everything at once now. So we're going to start. So in this case, we're going to analyze the row of the attention pattern corresponding to the word I. Right. So we have this, right? I've just moved the keys to the bottom there. This is annoying. Sorry, this Zoom thing is because I know that we're gonna use the whole screen.
Yeah, spread at the top. That's fine. That's fine.
Okay,
That's good.
okay, cool.
But yeah, like he was saying though, we are just taking the keys, moving to the bottom there, and we're just looking at one row of the attention pattern, right? So for a given query, I, we find out, exactly, how much of I, how much of like, and how much of cats will go into updating it, right? So what's happening there?
Sorry, I'm trying to. Oh,
It's okay.
Whatever.
You're good.
Okay, so yeah, we have this. So we're gonna so we're just gonna concern ourselves with the attention pattern for now, right? And basically what we see here is that in order to form the attention pattern, right, the model will extract a subspace, right, from I, call that subspace 1, right, and that creates the query. Model will also extract a different subspace
From
subspace
each of
2.
our different keys.
Right, and that creates the keys, right? Then as we saw, right, the model will do the dot product, the scaling, and then the softmax to create the probability distribution there.
Of the attention.
Exactly, which is the attention pattern for that row.
And now that we have this attention pattern, right, we can segue this in what we learned in the first part, right? Right, so now that we have our attention pattern, now we can use this to find out how much of another subspace can we use to add to the other subspace that we have, right? So in this case, we choose the subspace 3, right, from I like cats individually, okay? And then we're gonna take that, and then we're gonna multiply this, and then we're gonna add this to a subspace 4 in I, right? And this is what performs the update and updates our understanding of what I means now, right? So everything that's on this slide is what we talked about before we dived into the mechanistic explanation that we just gave right now. Yeah.
Right, so to recap this whole process, right? We have two subspaces, subspaces 1 and subspaces 2 that are used to create
The attention
the
pattern.
attention pattern.
Yeah.
Right, and then we have two further ones, subspace 3, which is then multiplied by 4. So subspace 3, from each of the embeddings, right? You then scale that with the attention pattern, and finally that gets summed, right? And then sent to a subspace 4 in the embedding for I. Cool so far?
Yeah, might be a lot taken, but do you have any questions at all? Yes.
Yeah, so when you add it back to I, then is this like done so that like doing this context to I will then change the context that's like used from the source embedding into the other destination embeddings as we move along?
So yes, so this process is not done sequentially. So we only show one row of the attention pattern here, frankly, because we don't have enough space on the screen. But
This is happening for all the other.
Yes.
places.
yes, yep, and and this will happen at the same time.
Yes, I am.
Do these subspaces have necessarily need to be disjoint?
Not
No,
necessarily.
they don't have to be. They might overlap as well. Yeah,
Yeah.
and we'll talk about this in a little bit as well.
Exactly. So just to remind, what's going on, right? Go. Yeah, and exactly. So to answer your question, these subspaces are different. That doesn't mean they have to be disjoint, but they could be, or they couldn't be, right?
But subspace 2 is one subspace. Subspace 3 is another one. Subspace 1, subspace 4 are all distinct, but they might have intersections, right?
Yeah.
Cool.
And
And this is kind of like the way information is flowing throughout the process of attention, right? If you will. We basically take, a subspace from I, that basically goes in, and that is our query. We take a subspace, from I like cats, which become our keys. We compare them to find out, how much attend to each token to another. And then that comparison is what allows us to modify our initial understandings and re-update them to our output values.
is this good?
Yes.
Just to be clear, when you say added to I, you mean like 4 is the space that we're modifying, like we're choosing.
Yes, 4 is the space that we're modifying. Exactly.
Correct. Yep. We add that to the subspace 4. Yeah. And the really important point here is that this pattern allows the model to compare different pieces of information from different subspaces in order to determine where other information should go.
So in other words, we take these two subspaces, we compare them together, and then based on what happens from that, we use that to take information from another subspace and move to a fourth one, right? So we compare two things down here, and this is to move, one thing from one subspace to another, right? Right.
And it turns out that this concept, the pattern allows the model to compare different pieces of information in order to determine where other information should go, can be a very powerful mechanism, right? Think about what you could do.
I guess in general, I want to invite, the audience to consider, when was the last time, you've seen something like this before? You compare two things together, and then you use it to, move information between two other things. Any example? Rafi?
You mean like an analogy? Like a relationship between two things can be applied to a relationship between two other things?
Yeah, sure.
Sure, anything.
You want me
And to be clear, right? So these subspaces we mentioned, they are different,
Right.
but only in the sense that they don't have to be the same. They could be the same, right? But they could also be different.
Right. There's a little bit of a peek there if you guys saw the screen. I think it's, yeah, you can just read it.
Okay,
Come on.
yeah.
All right. Yeah, if X is equal to Y, then P equals Q. Consider that simple statement, right? You compare two things together, and based on that comparison, decides whether or not you move information from Q into P, right? You set P equal to Q. Does that make sense? We're good so far?
Right. Similarly, if the current time is equal to my birthday, then the current activity is
It
my
might be
favorite
your
activity.
birthday. Sorry, it might be your favorite activity. But if the current, if the right time right now is my birthday, then perhaps my activity is my favorite activity. You're doing a certain action based off of a condition, right? So yeah, if the inquiry is a medical inquiry, then perhaps I should give medical records and not my transcript, right? So yeah, for example, this is basically the essence of what attention is doing, right? This is sophisticated behavior because you're basically able to make a certain assertion, you're able to make a certain judgment based off of some condition, right? And this is power. And we'll talk about why in a little bit. Oh yeah, we'll talk about why right now. So most of the time, we don't exactly understand like how a given attention mechanism functions or how it works, with other attention mechanisms, right? We don't really understand like what function it might be learning. But we do know that the ability to control information that's based off of other information, when you compose multiple attention mechanisms together, think about what happens when you compose multiple if statements within one another, right? You are able to implement highly generalized and very sophisticated algorithms which truly understand human language, right? So like by adding this ability to recognize context to our transformer, we didn't just let it, it's not just like adding semantic similarity that we did before. It's not just adding another thing to our many space. We have fundamentally given it so much more power than we ever did before. It can now logically reason. It can now logically think based off of a given task, right? It can learn and we've seen that it learns entire algorithms sometimes to solve certain tasks. And this is how it can do it, by composing multiple attention blocks together, by composing multiple attention blocks.
Yeah, so finally, the question of what's being learned, right? So when we train an attention mechanism, we're learning the 4 linear transformations, which are responsible for extracting and modifying the following subspaces, right? Those subspaces that we called 1, 2, 3, and 4. And so rather the names that you'll typically find, subspace 1 is called the queries, subspace 2, the keys, subspace 3, the values, and subspace 4, the output.
Right. Everyone good so far? Yes.
For the attention matrices, like, do they do that by tokens? So for our first example, like im would influence each of those, impossible would influence each of those, or is there a way not to like, or those accept?
Yeah. So each token will tend to every other token.
So
Right? But based on how we tokenize it.
So tokenizer that would separate im and possible, like im would influence.
In a hypothetical case where we separate the tokens.
That would help.
Yeah. And then finally,
Matrices are just transformations. We can basically represent our transformation that we talked about as distinct matrices. So formally, we will learn these 4 different matrices: the queries, the keys, the values, and the output matrix.
that's it. So come again. So we're gonna be having part 3 of this next time. So that'll be the last part. And then so today we went over basically what is the most complicated part of
This is the
the
hardest
transformer.
part of learning transformers, just this idea of attention.
Yeah. So next time we're
We're going to talk about like what the transformer picture is, how this attention is going to fit into that, and how everything goes. But we understand that today was a little bit of a lot of different learning curves. So we'll stick around for any questions that you might have at the end. And again, we'll post all information slides online. Text us, email us, whatever you need to do. Make sure you guys understand this stuff because this is the key to transformers. Yeah. Thanks, guys. Appreciate it.